Thanks a lot. Okay.
Please, Filip.
Thank you. Thanks a lot for having me here and for organizing this event. So I'm gonna talk about also about quantum measurements, but in a little bit more applied setting, namely about modeling the measurement noise in the quantum devices that we have now. So this is a joint project with Janek Tuziemski, Oskar Słowik, and Michał Szmaniec, all of them being from Polish Academy of Sciences, and Michał Szmaniec is the group leader. Okay, so here's the outline of the presentation. I will start by brief motivation and discussion on how to model measurement noise. Then I will introduce operational measures of correlations in readout noise and explain how to efficiently learn the readout noise models from the experimental data. And I will finish with discussion of noise model benchmarks that we performed on like actual systems of over 100 qubits. So the motivation is actually quite simple, namely readout noise is there and it is significant. So this is a cumulative distribution histogram of errors from Google's famous quantum advantage paper. The readout noise is here in orange, and as you can see, it is quite high, even compared to like to 2-qubit Pauli error rates, so like 2-qubit gate errors. So they write here that average readout error is on the level of around 4%, and in practice I've seen even much higher figures in actual experiments, for example on IBM's machines. So in general, this is a significant source of errors, and it makes sense to develop methods to characterize it, which can help, for example, for some error mitigation. If you know noise model, then you can try to somehow reduce the errors. Okay, so I hope you are convinced that it makes sense to study this, and now let me briefly describe how we can model readout noise. So in previous presentation, we learned that in general, in the most general like quantum measurement that there can be, like, so also used for like modeling of noisy measurements, of course, is called POVM. And if we consider like noisy measurements on the system of n qubits, then like in general this will be described by 4 to the n parameters, which is quite a lot. However, it has been observed that in practice it is often the case that one can model the readout noise purely classically, so to speak, as a stochastic process applied to measurement outcomes, and it has somehow lower number of parameters, still high. So let me explain what this classical noise means with a single qubit example. So say we prepare a zero state and we measure it in a standard basis. So we clearly expect that the measurement result will be 0. And this would be the end of story if the measurement was ideal. But in reality, we have some noise, some classical noise, and this outcome just gets relabeled to some other outcome with some probabilities. So we have a blue probability of correct labeling and a red as mistaking outcome, which should be 0 as well. And if you want to construct a stochastic map that describes this noise, you basically just put those numbers in the first column, and if you want a second column, then you just put a one state for 1 qubit. And this was just for 1 qubit, but of course you can generalize it to more qubits just by putting like more computational basis states. Okay, so in general, we have a situation that on a noisy device, we sample from a probability distribution that is related to the ideal distribution that we would like to have access to samples from by some stochastic map. Okay, so on an actual quantum device, like described by this classical noise model, we will have access to samples, so the measurement outcomes from this probability distribution. Unfortunately, so in this scenario, the task of noise characterization kind of boils down to characterizing such stochastic maps. And unfortunately, without any assumptions, this is exponentially hard with the number of qubits, which is a big problem. But the possible solution that we look into in this project is to study noise models that are correlated but local. So in what sense? In this setting, the global noise matrix, this lambda, that affects the whole noisy probability distribution on all of the qubits, is a tensor product of some local noise matrices acting on subsets of qubits. So we call those subsets clusters, and this corresponds to a situation where some qubits are strongly correlated with each other, namely those qubits that belong to the same cluster, like for example here or here. And at the same time, they are not correlated at all to other qubits. So this is how it looks like. So like those error probabilities basically just multiply themselves like between the clusters. Of course, in reality might be just an approximation of what's going on. The question is whether it is a good approximation. So having the above in mind, now I can say that in this presentation, by learning the noise model, I basically mean reconstructing the cluster structure. So this tensor product of those lambda noise matrices. Now, if I want to learn local correlations, so this local noise model, what can I look at? Well, recall that in quantum device, I have access to samples from such a noisy distribution. But then if I am interested in some local correlations, I do not really know to study the whole distribution, but perhaps I can just look at the marginals of this noisy distribution to look at the local properties of noise. So how can one use marginals to get information about correlations? Consider a single qubit detector on qubit I here. So if there is a crosstalk, so like some correlations in readout noise, in general, the noise that describes this detector will actually depend on what happens on the other qubit. So for example, whether you insert there a 0 or 1 state. So depending on the input state of this other qubit, you will have different probabilities describing errors on qubit I. So those noisy distributions will be different. This 0 and 1 just indicates the state of 0 or 1 on another qubit. So now one thing you can do is to use the difference between those two noise models as a measure of correlations. So a commonly used distance in statistics is a total variational distance. And here we also use it to quantify how much the noise on qubit I differs due to the state of qubit J. Specifically, we define worst case measure of correlations, that is a maximal difference between those noisy probability distributions, depending on the input state on that qubit. Depending on the input state like of the qubit that affects the noise on our qubit, and we maximize over all states on this affected qubit. So this is like the worst case scenario that like how much the statistics on the qubit I can differ due to the effects of correlations of the qubit from the qubit J. This is the idea behind it. And so this is like the worst case scenario because we maximize over all possible states that I can measure on the qubit I. But also we can consider an average case measure, which tells you what is not the maximal difference in this total variation distance, but the average, where the average is taken over pure states on this qubit I. Okay, so to learn a noise model, we can look at the marginals of noisy distribution and estimate correlation coefficients defined by me just a moment ago. Then what we do with it is, well, we basically just plug this data as an input to some heuristic optimization procedure that we developed that aims to find a cluster structure based on just two-body correlations. So this is like just a general idea. I'm not going into details about this, but it's just like some heuristic optimization. So pictorially, learning of noise model in this project essentially consists of 3 stages, namely experiment design and implementation, data post-processing, and model verification. So I already told you like what we do with the data, namely we use this correlation coefficients to get a cluster structure of the noise model. And now I will answer the question how to get that data. So the type of experiments that we perform here is called quantum detector overlapping tomography. And the idea is very simple. So you basically do something like a normal tomographic reconstruction, but in parallel on all subsets. So I will explain what I mean by that. So imagine that you would like to study noise on k-qubit subsets, okay? So like, for example, you can think about pairs. So I already told you that to characterize this lambda, you need to insert all of the computational basis states. So if you have some k-local subset, then and you want to like reconstruct kind of a marginal lambda on that subset, you need to put in all of computational basis states on that subset. And this is what I mean, like a full tomography. This just means that you like fully reconstruct this noise matrix. And in this case, on the k-qubit subset, you can think, for example, about pairs. So what you could do, like say naively, using like a normal tomographic approach, is well, you would take all of the k-qubit subsets. So if the device has n qubits, it will be like scaling like n to the power of k, and put all of the computational basis states in there, so 2 to the power of k. So this is like the simplest thing you can do, but it's also very inefficient in a sense in the system size. So I mean, it's polynomial, so it's not terrible. But of course, if you have like a 100 qubits, or maybe we'll have some 1,000 qubits in some not so far away future, then it might be significant. So we always aim to like reduce the number of experiments. And in this approach, you basically, if you allow for doing this not separately but in parallel on multiple subsets, you get exponential reduction in the number of circuits. So now it's still like the number of circuits that you need, it still depends exponentially on the locality, so on the size of those k-qubit of the subsets, but it only depends logarithmically on the device size. So this is very good. What it means in practice, for example, if you want to characterize all pairs on 125 qubit device, naive strategy would require you to do like 30,000 circuits, but here you can actually do it with something like 40. So this is very, very nice reduction. So basically, this makes this procedure very nicely scalable for like any system size, provided that you want to like characterize only small kind of local correlations, that the k is not too high. So the size of those subsets that you characterize. So one might ask how to choose the circuits in order to perform this tomographic reconstruction of the subsets of locality k. Well, it actually turns out that a good idea is to just apply gates randomly, and in this case, those gates are just like X and identity gates, because this is you usually start with a 0 state in a quantum device, and then you want computational basis states in there, so you apply randomly on each qubit X or identity gate. And one can show that for such a randomized construction, in order to characterize noise matrices on all k-qubit subsets up to some error epsilon in matrix elements, it suffices to perform number of experiments that scales like this. So this is what I was indicating on the previous slide. This is for a classical noise model where the noise can be fully specified by a classical stochastic process. And for general quantum noise, the exponent changes, the base of the exponent changes to 6. So it's more complicated, but still the logarithmic dependence on the system size. So just to convince you that it is doable, here are some experimental results for correlations characterization of 109 qubits of an IBM system. So there are like 2 points here. This is like the graph shows like a this is like a topology of a chip. So all of the nearest neighbors are can be entangled directly with each other. And what you can see are those arrows, which indicate how much, how big is the magnitude of those correlations that I defined previously. So how the state of one qubit affects the statistics on the other qubit. And this is a scale. So what you can see there, I mean, it's not like there is a super crazy amount of these correlations, but there are some, and they might be even as strong as like 20%. And also what you can observe is that some of them are non-local. So on this graph, we plot only those between nearest neighbors, and here you have also some more correlations. Okay, and a very similar graph for Riget the Aspen M1 device. With here we studied 55 qubits, and yeah, it is a little bit more complicated, but the message is similar. Okay, so I told you that we can do this detector overlapping tomography, get correlation coefficients, and reconstruct the readout noise model. The last question I will attempt to answer now is how to verify that reconstructed noise model. So how to check if it agrees with the data. Okay, so we now assume that we have already characterized the measurement device, and we have some noise model that we want to benchmark. And the benchmarks we propose are very simple. We put inside the device some separable state, psi I, and estimate energy of some local Hamiltonian Hi on the noisy device. Okay. So since the device is noisy, the energy estimator is going to be noisy as well. And now we do the simplest thing. We basically simulate this noisy energy and check how well it agrees with the experiment. So the choice of separable states and local Hamiltonians is kind of twofold. So first of all, to prepare separable states, you need only single qubit gates, and they are usually of very high quality. So if there is a noise, in this experiment, it will be mostly due to the readout noise. So this is what we want to study. We don't want to dilute it by some other type of errors. And also because we want to be able to actually know what the energy should be, right? So the noise model that we have is like local, so it has an efficient description, and then separable states also have efficient description, and so we can check what this energy should be on the computer. And there is also an alternative benchmark that we do, which is a little bit more fun and like more kind of focus on applications of this all of this noise characterization. Namely, if you have a noise model of this type, you can actually use it to construct some procedure of post-processing your data from some experiments like this Hamiltonian energy estimation to correct this data. So you can kind of like inverse the effects of the noise on your data. And the idea here is that if the noise model is good, then we also expect that error mitigation based on that noise model also should be good. So this is like just a reasoning, and so basically what we do is we estimate energy on the quantum device, and then we perform error mitigation based on the noise model that we want to benchmark. So in this way, we both benchmark how whether the noise model is good, and also whether it is good for error mitigation, which is like one of the most important applications of noise characterization. All right, so the last slides are with the experimental results. Again, on IBM, we did experiments on 109 qubits. What you can see is like again cumulative histogram, like on the first slide. So the x-axis is absolute energy error per qubit. So we divide it by the number of qubits to have like somehow system in size independent figure of merit. So this is like just a difference between the error mitigated value and the ideal value of energy. So what you have in experiment and what you should have. And here is like just a fraction of Hamiltonians. It was like a few hundreds of them implemented. So the red line is experimental data which is uncorrected, so it's like just noisy energy. As you can see, it's the errors are pretty high for this energy estimation. This line corresponds to median of the results, so it's like on the level of 3%, and this is per qubit, right? And then if you do the noise mitigation, but based on completely uncorrelated noise model, so you just assume that none of the qubits talk to each other in the sense of readout noise correlations, then you will get this magenta line, this second one. So it corrects a lot. It's pretty good. But if you use the noise, this a little bit more complicated noise model that you still can efficiently characterize using those methods that I introduced, then you have even bigger reduction. So this is like quite a significant factors here. Okay, so those are results for IBM, and also like similar results for Aspen. Basically, I mean, the noise here is bigger. We also made lower number of experiments, so there is a little bit more of statistical noise here. But generally, I mean, the errors are huge here, and you can see that that similarly as before, the error mitigation based on uncorrelated noise model is somehow worse than the one based on the correlated noise model. Okay, to summarize, what I talked about is a probably efficient method of learning readout noise using detector overlapping tomography. I introduced some operational measures of correlation. So operational, I mean, they have just clear interpretation in terms of statistics. And I talked about like finding the noise models based on this idea of clusters, so like small subsets of qubits that are correlated with each other. And I have shown some experimental results of noise model benchmarks for a system size up to like 109 qubits. If you're interested, we have some of those ideas implemented in the GitHub repository. There is also a previous paper that talks about it, which is this one. So thanks a lot. And that's all from my side. I'm happy to answer any questions.
Yes, thank you, Filip, for the interesting talk, which is now open for questions, comments. And if it is not the case, we'd have time for the small coffee break. Thank you, Filip, once again.
Yeah, thank you.